Hands up for like project managers, architects, even that could be also developers as well. All right, architects, more executive style decision makers about investing in technology. Okay, anyone else I didn't really cover who wants me to know that they are here? Data scientists. Oh yeah, former life. I'm sorry, I forgot you because that. Okay, anyways, all right. So that's a good collection. I think this will be this talk is a little more high level than I'm used to doing when I come to Graph Day and Day to Day. We're going to kind of go through what I'm kind of calling my journey through life in the trenches with graph databases, and I have this targeted more towards the architect persona. More towards people who are making decisions about if they need a graph database for their problem. And as I saw this talk, when we were standing here, we were at the Day-to-Day 2016 in Seattle. Seattle's a November conference, I think. 2016 in Seattle, Lynn Bender was all jazzed about 2017 being the year of the graph. So we just had that. The year of graph just went by, and there's a lot of projects that I was personally architecting or I've been involved with that I learned some very valuable lessons as we went through the year of the graph. And I wanted to take this talk to kind of capture those lessons learned, tell you all what I found to be successful, also tell you what I found to not work and basically fall over, and kind of walk you all through my mindset when I'm approaching a new problem and how I qualify it if it should be used in a graph database, graph analytics, etc. So that's kind of what I hope to go through today in this talk. Are you guys good with that? All right. As I see it, this is what just happened in 2017. Everyone was like, it's a graph problem. Just shove the data in a graph database. It's magical, and we're going to get these unicorns of useful information right back out of it. And when we were going about tackling problems, and I very much was involved in that effort, sorry, but we really didn't connect together the utility of a graph database and what they really were going to be useful for. And so, like I mentioned, I'm going to kind of go through my mindset and how I classify new problems, how I look about determining their architecture, and figuring out what's the best tool for solving this problem. And I feel like most of the days I'm looking at problems saying, no, that's not a graph problem, that's not a graph problem, and that isn't either. So maybe I'll help you guys in perceiving that. But for those of you I haven't had the opportunity to meet, I kind of wanted to also just let you know my journey that led me to getting to be here with you all today. I started off with an undergrad in mathematics, emphasizing elliptic curve cryptography back when Bitcoin was fun in 2008. And after that, I went to do a master's. And my first semester, I was registering for classes, and I got locked out of all the classes I had to take to actually complete my master's. And there was one class open, and it was called graph theory. And it was all I could register for. So on the first day, I'm dragging my feet going into this graph theory class, thinking I'm going to be learning about like data visualization and the theory of like pie graphs and bar charts. And lo and behold, it was taught by Dr. Teresa Haynes, very renowned graph theorist in the community. And within the first few moments of class, I felt my whole world just open up with how you can do different data modeling and problem solvings with graphs. And so since then, I continued on to do my PhD in computer science and was a very heavy user of Titan starting in 2015. That's how I got to know Matthias and the Aurelius community. And that led me to now being a senior graph consultant and architect for DataStax. So that's kind of where I am, and been a part of many different deployments and uses of graph databases. And I kind of wanted to capture all of that into how I approach a mindset of qualifying if it's a good graph problem and what types of tools you should use. So this is purposefully really gray, and I think the text will be okay. It was pretty small on my screen, so sorry for the folks in the back. But the agenda of this talk is essentially to walk through these 3 decision points that I go through when I'm looking at a problem. So basically, if you had to take a picture of what's inside my head, it looks something like this, and we're going to kind of walk through that today. And where this all started for me, where I started developing this mindset of decision making, it all started with the graph and wanting to build that one database that was going to collect everything. And you were going to put all of your data into that database, like I mentioned, and you were going to get back all of the information you ever could imagine. And when you start to envision what that looks like, it's pretty easy to start to understand what you might be able to do with a graph database. And that's where the journey started for me back in 2015. I was at a healthcare company, and I think a lot of the day-to-day and Graph Day attendees have seen me here talking about what we were building with the health graph database. And this is really the big vision. It's the big vision that almost anyone has when I talk to them about wanting a graph database. They have people, they have businesses, they have doctors, hospitals, and they know that that centric entity has useful information about it. And if we could just connect that central entity to other central things, it would be a really useful way to start to learn things about our data. I get it. I love graphs, and I think that's a really great way to use a graph database. But where we started, and where I'm sure most of you all are as well, is it looks a lot like this. You've got data in these different sources, and you most likely don't have a strong ID or like a nice UUID that you actually trust, like truthfully really trust, to link you from one set of data to the other set of data. And so we really start with a problem that looks a lot more like entity resolution, to be able to get the data out of one source and into the other source. And when you're starting your problems from this way, you've really got to think about, well, what do I really need? We have this big vision of wanting to coalesce all of our data into a graph to connect it from one entity to another. But right now, where I am, I've got data all over the place in my system, and I don't really understand what's there. So for our data scientist here, what are the distributions of features that I have? How many different things are even in my data? And when I was going down this journey, after a little bit of picking up Titan, I realized that on the project, our decision makers really needed answers to questions like this. So when you're in healthcare, you don't have a strong ID that you really can use to match patients from one hospital to another. A lot of enterprises don't have strong UUIDs that are going to be able to match your one entity to another. So we were more concerned about questions like this. Across all my data, I mean, how many different keys and values do I have? And then for each of those values, what's their distribution? How do I know if I can even match one thing to another? If I were to look in this window of time, how much of something occurred? To me, when I'm asking these questions, I don't see a graph. I see things like this. I see that we need to understand how many of something happened over a certain window of time, or maybe you're just talking about revenue, slices of revenue or something that happened over a certain window of time. And if you're getting more into the entity resolution side, you have like a payload of data, you've got some first names, last names, some addresses that are probably fat-fingered. And really at this point, we want to use technology that's probably better suited for like a TF-IDF approach for doing searching and finding similar entities. And so my story with Titan, when I was working with it at this project, we started with this big vision of wanting to coalesce all of these entities together because it would be really useful to derive the linkages from one master entity to another. But this is actually where we were. We needed to understand the data, and we were trying to skip over that and build out a graph database and just slam it all in there because it was going to work and it was going to be great. And regretfully, this is not a graph problem at this point. And what I want to really impress upon you all is that when you approach your problem and you don't fully understand the path to get there and where your data is, you might not have the right tool up front to solve your problem. For us, when we were building this back in 2014, 2015, 2016, ultimately the use of the graph database to solve these problems, it didn't work. And so that was the day that my life turned gray, when we had to turn Titan off in prod and I had to go use another tool. And for me, that was a really sad day. But that's just one way and one part of the lesson that I kind of wanted to bring to this audience, to make sure you really fully outline when you're working with your project, you understand what you need to get back out. Because if you get the right tool in the front to begin with, you ultimately might end up in a kind of project failure situation, which no one really wants to be a part of. And that leads to the first little decision part. If you were to kind of peer into my brain from the experiences I've had with building different solutions, it's this first little decision part where you're saying, all right, what does my problem need? And inherently, what I'm saying here is that if you really need to be discussing only like data analytics or business analytics or pie graphs and things like that, if you're searching for things, I get it. Yes, we can do that in a graph, but do you really want to? Do you have to? Is there a longer journey in which using that information to build a graph is coming? But where should you start? Consider those things. because you don't want to necessarily bring in the most flexible do-all hammer up front. It might lead to a project that's deemed not successful due to deliverables and actually providing business value if that's where you're starting, what's on the right. So from here forward with the rest of the talk, let's just level set and assume now that we have graph data. We've had those difficult conversations and we've found a few problems that really are graph data. And that's where we kind of start going to the right. And now it starts to ask, now you need to start asking questions, well, what are we doing with this graph data? And that's where I want to kind of introduce a little bit of a problem. What I'm going to have you all do is I'm going to put a little brain teaser up here. And I want to see how you all would solve this problem. I want to just think through it for about 30 to 60 seconds. We'll kind of go through what's happening. I'll give you all 30 seconds to think about it. And then I'm curious for anyone who's brave enough to just kind of shout out how you would approach this. And so here's the problem. We have a scheduling issue. We have a Bryn lender, no relation, who's organizing a conference with 4 speakers who flew all the way from Winterfell. And these speakers had some logistics issues for making their conference talk happen. And you can kind of see the 3 logistics issues as you go down. So the first one is that Arya and Sansa, they can't have their talk at the same time because it requires the same room. And then Bran and Rob's talk also is in the same room. That's the first constraint. The second constraint to our scheduling problem is that Mr. Lender doesn't want to have Bran and Sansa's talk at the same time for whatever reason. And the third constraint is that Arya and Bran have to help each other with their talks, so they can't present at the same time. So I want to challenge you guys to take the next 30 seconds, just kind of outline in your head how you would want to solve this problem and what you would do to solve it. Anyone brave enough to shout out their approach? Go ahead.
Draw it into a table.
Draw it into a table, and what would you do with your table?
Put time slots and put name slots, and then just put them next to each other. And if people are on the same time they shouldn't be, move it.
Move it. All right, so brute force. Table, brute force. I like it. Anyone else? Go ahead. Okay. Integer program with constraints, kind of doing like a greedy algorithm approach. Cool. Yeah. I'll go ahead and show you how I would approach this. Under the pretense that I told you the slide before that I was going to approach everything else as a graph from here on out. So I'm sure you all saw that was coming. So here's how I would do this. I guess my whole point, though, at this point is that I've got to convince you that this actually is a graph problem and that we do have graph data. And so here's what we would do. I would start this up by determining the things that need to be scheduled. So we have 4 talks that need scheduled. And I would put those as vertices in a graph algorithm. And what I need to do now is add edges to my graph. And the edges in this graph are going to represent a conflict graph. You put an edge between 2 things if there's a conflict. So the first constraint we had was that Arya and Sansa, their talk required the same room, as did Bran and Rob's. So you draw a conflict edge between those pairs. The next constraint was that our conference organizer, Mr. Lender, did not want to have Bran and Sansa's talk at the same time. So I take that constraint and I turn it into an edge in my graph. I just draw an edge between those 2 people because there's a conflict with having that at the same time. And the last constraint was that we had Arya and Bran helping each other with their talks, so they couldn't have them at the same time. Clear as mud, right? All right, so how do we actually turn this into a scheduling problem to where we've answered the original scheduling question? Because remember, we've been challenged to determine a way to schedule the conference. And as a graph theorist who loves all things graphs, what I would do is I would color this. I would apply a chromatic number algorithm to this graph to determine how to schedule it. Some are spatial and some are temporal, but at the end of the day, it's a conflict about time. So we're creating a conflict graph, creating an estimation on time and scheduling time. All conflicts are useful. All conflicts are needed for when the time of that talk has to happen. But you're right, some are spatial, some are temporal. So to color this, chromatic number, start with aria. I'm going to just kind of walk through the graph. You can give aria an orange color. And a chromatic number, when you do a coloring algorithm in a graph, when you take two vertices, or any vertices in the graph cannot have the same color if they have an edge between them. That's what a graph coloring algorithm does. So you start with aria. Aria is orange if the colors are showing up okay. You can walk over to Bran. Now, Bran is adjacent to aria, so Bran can't be orange. We're going to give Bran a new color, teal. And when you walk over to Sansa, Sansa's adjacent to both an orange and a teal vertex, so we need a new color. And we're going to go ahead and just assign Rob that same color because Rob's only adjacent to a teal vertex. So what we've done is we've colored our graph. What we can do with the coloring of the graph is you can look at the vertices that are the same color, and those vertices or those talk sessions can happen at the same time because there's no conflict. And that's how you would look at scheduling a conference. The teal vertices could be session 1, the orange vertex could be session 2, and then the dark purple / black could be session 3. I've seen this applied before for kind of scheduling operations at a hospital. Operations are what you need to schedule, and then we have multiple constraints, either technology, personnel, rooms, times, and an edge is an edge. There's a constraint as to why those two operations can happen at the same time, and it gets pretty large. And when you do an example, just kind of a brute force coloring algorithm, you have a way to schedule the operations of a hospital. Just a unique way to apply chromatic numbering to solve a real world problem with graphs. But what we have here, when we have graph data, is we have graph analytics problems. When you're talking about these very unique ways to represent data with a graph and do a full traversal around it potentially, we're talking about graph analytics problems. And these are some of the most interesting problems, or the most easily visualized. And these are some of the questions that are really common when you start to run into graph analytics problems. You can have things like, from one city to another, what's my shortest path? We've all seen that a million times. There's also a really great blog out there for the adventurists who want to visit every national park in the United States. There's the optimal path, because they ran a traveling salesman problem on a bunch of computers to determine it. If you haven't seen it, look it up and then go hit the road for 2 months and follow the path. Traveling salesman problem, very complicated NP-complete problem with analyzing graph data. And the scheduling one we just went through, and then an interesting one that I can talk about later for anyone who's interested is a way to apply graph dominating properties to put fire alarms in a building. That's a very interesting way that I worked on with my master's thesis advisor on way to use domination properties of graphs for that type of application. The common algorithms for graph people in the room, if you're interested in diving further and like getting a few things to start Googling, this would be where I would start. I would look up maximum cliques, clique being you have vertices and every edge is present between all of those vertices. Chromatic number, we just went through, the coloring of a graph. Vertex degree distribution, that's where you just understand how many edges are incident to a vertex and understand what that's like for a global graph. PageRank, a lot of stuff you guys have seen. And so in my head, this is where I am. We have this concept of determining if your problem even needs graph data or if it just needs more business analytics summaries. And so once we have our graph data, you need to really understand what it is you need to do with it. The chromatic number example or PageRank or things like that, those are graph algorithms, and you want to make sure you're picking tools that enable you to solve these large graph algorithmic properties within the expected time that your application has. Which leaves us left with one bucket. And that bucket is, well, there's graph databases and we're all using them. What are they good for? Because we haven't gotten there yet. And there's two applications that I want to spend, about the next 15 to 20 minutes kind of walking through two successful applications of graph databases that I either have built or have helped advise and build throughout my time working within graph analytics and databases in the past 5-8 years. The first of which is graph-based entity resolution, and that is a mouthful. This problem actually came about as a part of my research for my PhD, and it just so happened that after applying every machine learning algorithm I could at my data set, it just so turned out that the features that represent structural data, the connectivity between my data elements, that was the best way to do my classification for this problem. So what problem was I working on? I had now 350 million cell phone numbers, and then they're call detail records over a few months of time. It was a pretty interesting data set I got to work with. And the goal of working with that data set was to predict if you left the network where you went. So, I mean, we all have cell phones, right? We're all on a network. And if you choose to leave your network and you keep your same cell phone number, which most Americans do, it's a very easy problem, because in the call detail record, you'll have your same number and it'll just change the flag, like Verizon, AT&T. You make my life easy when we're trying to do this. But for most cultures, most people actually change their phone number, and they'll decide once they leave Verizon or leave whatever company, they're gonna go ahead and change it. And that's where life gets really hard, because you can't call up the new number and say, oh, hey, did you have this number before? Because that's a little illegal. So what we did instead is we did a lot of research on machine learning algorithms to determine, well, how do we accurately predict where you went? And so to continue to illustrate the difficulty of this problem, consider you're the Teal network. Consider you're the Teal Telecom network, and you're trying to analyze their call detail records. You only have the ability to look at the data that either originated or was received by somebody on your network. So you'll never see edges between the orange and the dark purple vertices up here. You only have the edges that start with a text or a call that started with or received by a blue vertex. And the way I kind of trained this algorithm is I had 4 months of data, and so I sliced it up with training sets where I knew the person was present in both the month that I was looking at and the month I was trying to predict. Just basic training for doing machine learning. And after attempting, support vector machines, singular value decomposition, and neural nets, it just so turned out that this approach was the best. And here's what it was. What you do is, let's say that this blue vertex on the right, this phone number disappeared during the next month. And so we're gonna find them. You'll go to the month they were last active, and you collect all of their friends that are on your network. Again, because you only can analyze calls and texts that start or end on your network. So you'd collect all their friends, and we'll say in August 2017, the guy we're trying to look for had 5 friends on our network. What you want to do now is you want to build up a friends of friends list on who their contacts were when we lost them. And that's how you'll start going through that center list. You'll pick your first one and you'll say, let's collect their friends that happened during September. And you can keep going down that friend set and say, give me their friends that were active during this window of time. And you can eventually build up what we would call a candidate list. So here's your candidate list. So what's happening up here is we have this blue vertex on the right, and we know that they disappeared during this month of time, and we're trying to find them. So we collected their friends and then the friends of their friends to determine the candidates of who they could be. And so now it comes down to a ranking problem. Who is most likely that person? The algorithm ended up being whoever had the most friends in common. You are who your friends are, and it is never more prevalent than today. So the next question is to say, well, how good are you at doing this? Like, come on. Like, really? Is it that good? And here's the punchline. If you see red, if your data behavior falls in the red, we found you. See red, you're dead. That's kind of how the punchline here worked. So what is this showing? On the y-axis, going up, we have something called an attrition rate, and this was over a 2-week period, so 2 weeks of gathering and 2 weeks of predicting. The y-axis is your attrition rate, meaning what's the likelihood that you're not going to be active during this 2-week window? What is the likelihood that anyone in here is not going to call or text somebody for 2 weeks? So what this is saying here, this is 20% likely that you're not going to be active at all during 2-week window, and this is 80% likely that you won't have any activity on the network in 2 weeks. And then this number on the x-axis on the bottom, that's the number of unique contacts you had during that window. Just unique, not total activity, just straight up unique contacts. The percentage of how good this algorithm is shown in that color scale. So the dark red essentially was about 96% or better at identifying people on the cell phone networks according to this approach. And the reason I kind of wanted to walk through this is that when it comes to entity resolution, which is becoming a very, very popular problem now that we've been working with graph databases, I would love to talk with anyone here who has found other ways to make entity resolution successful with a graph database, like a purely relationship-based approach to entity resolution. Because for me, across the studies I've been doing, this has been the one most successful way I have seen telecom companies actually do entity resolution purely with graph data. So another sidebar that we can have afterwards. And the last example that I kind of wanted to walk through today was a way to view your graph database as like a master identity store. So let's kind of rewind a little bit to where I started with this problem. And we started here. We had that big vision of wanting to coalesce master identities into this single master and creating relationships from one master to another. That's kind of what we're trying to do. And when you approach using a graph database for like a master identity store, we're assuming that the entity resolution has happened elsewhere. If you happen to be a telecom company, sure, you can use a graph database from extracting your data, putting it in a DB, and the entity resolution part. But most likely, at this point, we've done entity resolution probably in Spark, or a system that's better handled for semantic inferences between character edit distance and stuff like that. So the question now comes down to, well, if we want to store the way that our entities are represented in our different system in one database, what do? I started here. This was terrible. It did not perform. I've seen other people do this too, so I kind of wanted to share you what a graph schema could look like. I started here. I thought conceptually it would make sense. Like, I had this person from this database, and they had that information. And then I have this person from this database, and they happen to be the same, so I'm just going to put an edge between them. And then I'm going to add yet another person who is the same, and now I've got a clique happening of the fact that all of these people are the same. Think about what that model would be like when you're reading it. If you're trying to query your graph and say, I need the person out of my graph database who has this feature. You're not pulling one, you're pulling three. Because G.V. has a first name, last name, it's going to pull all three of those person vertices. And now imagine what that traversal would look like in your head if you needed to start going down their neighborhood. You're not just working from one, you're working from all three. So all three of those master persons has to be connected to their friends, and your traversals already start off with a constant time factor to your branching as you go down in your gremlin traversals. I wouldn't recommend this model. It's a little too heavy, and maintaining these cliques becomes a little more difficult. And it comes back down to this question again. What are you trying to read? What do you care about if you are trying to resolve your entities into a graph database? Let's pick phone number, for example, because phone number, as an example, I remember having a very heated debate about it, and whether or not it should be an edge, it should be a vertex, it should be a property in my graph. I mean, this was like a heated debate that went on for way too long. But think about it. Is it useful in your data to connect a master identity to another master identity according to a shared phone number? Telecom example is the answer is yes. Healthcare? Maybe not. Fraud? Maybe yes, because you could be potentially using burner phones and illicit networks to do your fraudulent activity. So you got to think about that. If connecting people according to a property is useful, that probably needs to be a vertex. If it isn't useful, you can just put it as a property on your vertex, or you can not even put it in your graph database at all. But this is where I'm going with this. Once you start digging in and you think about coalescing the different identity data across your sources, you're going to have that natural debate about what becomes a vertex or a property or what comes in here at all. And so this example up here is just an example. You want to end up with a master person vertex that links to other master person vertices, and you might need to make properties that are vertices because it's useful to connect your people through those properties. For your application, if connecting via address doesn't make sense, I would not recommend going through the address denormalization process in a graph database. It's not an easy one. I would love to find any enterprise system that actually just represents states as something consistent. The 2 letters or the full name, like anything. Any kind of consistency would be great. It never happens. So there's a lot of ETL that happens to even get it to here, and you need to understand that, and you need to understand the weight and the complexity it takes to even get here. So this is one way to think about it. You can picture those multiple databases that you have, and you know your goal is to get here, but be picky. Be very limited. Only bring into the graph database what is useful for extracting relationships from one entity to another entity. When we got to this last time, when I was working on graph architecture here, we realized that we're losing something that's pretty important. And that was the provenance of where this data came from. So the data engineers in here, hopefully you're kind of starting to get a little sweaty or kind of concerned at this point because like, well, where did this data come from? And that's one way you can maybe go to a next step. Again, it depends on your application. Do you want to leave specific pointers in your database, in your graph database, to the origin of the data? Is that not a useful way? Definitely, I would not recommend leaving some graph form of all of your data. I would just leave it in its original form, leave it at where it is, and use the graph database to model the relationships that exist across the data. So what we see here, what I added onto this slide, was the fact that this master person was extracted from some source, some provenance, some payload somewhere else in your system. And making sure that you have the accessibility to that full raw data, that's useful. Bringing in that full raw data payload into a vertex just because you can, maybe not so useful. Another way to think about it. And this kind of starts to bring us back into when I come onto a project or when I receive a new problem to go through. This kind of brings me to these two main questions. Always remembering, what does your problem need? And if you know you have graph data, what are you going to do with it? Are you more interested in creative uses of graph algorithms, like making a bipartite graph to do matching, or the graph coloring example that we went through for doing scheduling? If that's not what you're looking for, is it that you know that there's a vertex and you know that like a few edges away there's another vertex that you want to get access to? That's clearly just a database read. Graph databases are not unicorns. They're databases. Use them as databases. That's what they're there for. And even better is that when you're modeling your data in your graph database, you know where you're going when you're writing your traversals. You know where you start, and you know the path that you need to go to. You can think through the various systems you've touched, maybe even some SQL that you've written, where you've written that SQL code that no one else could understand, but it was beautiful and it worked. But it also had maybe 5 or 6 different types of joins, an inner join, a left join, all that. If you can think of that type of join that exists in your system now, that's going to be a great candidate query to port over into a database, a graph database, because that's where those edge traversals are going to be able to get you that information out in hundreds of milliseconds, instead of however long it takes your system to do that massive join across all your data. And this all sounds really great, and you all could be thinking about the problems that you have, and you might not be able to break it down into these buckets. But the whole point here, though, is that if you can't break it down into this is my business analytics need, this is my search problem, this is my graph analytics I want to do, and this is definitely a graph database problem. If you can't break it down into those components, I would recommend that you keep going. Find another subproblem that you have within that and go after that. Make sure that you guys are breaking these things down and using your architectures to have the right tool for the right problem. And this is a critical moment for the graph database community. I think it's a critical moment for the graph database community because, like myself, we approach this like the unicorn solution to our data problems. And there's been a lot of unsuccessful implementations that I know I was even a part of. And if I could have kind of gone through this process with the lessons I've learned previously and done it over again, we would have had a lot more successful implementations of being able to construct these graph databases to be able to get out some much more useful information. So my punchline here at this point is just that the ramification of the decisions that you make with your architecture, they can really make or break your full application. And you need to understand what it is you need to get out. You need to understand the data. You really need to take the time to understand the distributions of what's there, how you want to model it, and how you want to get it back out. Really just use the right tool for the right problem. And so that is kind of the conclusion here of what I have to say about graph databases, and that not everything is a graph problem. So thank you all for coming. Do you have any questions?
So the previous slide, where you branched
Yep.
Say, so we might want to benefit from using graph algorithms,
Mm-hmm.
which means the underlying storage could be any with over storage, right?
Mhm.
It's not a graph database.
Correct.
Just solid implementations of graph
Yep.
algorithms on top of it.
Yep.
And the other side is a graph database where the nodes and entities relationships are provided to you, but they don't necessarily have implementations of those. Are there such things which are graph databases but do not have graph databases?
Yeah, I think that's a great question, and to just repeat it for the people in the room, he was mentioning that here on the graph algorithms side, you have the way to run graph algorithms not necessarily in graph databases and other forms like matrices and things like that. And then on the graph database side, you inherently are storing things in a database as vertices and edges. And so the question is, have I seen problems that are graph databases that don't need graph analytics? Did I repeat that right? And so I actually have seen a few very successful implementations where we had, I love the graph words. We had a galaxy within a database of different stars. And that's actually real graph theory words. I love this. So a star graph is a vertex in the center, and then you have kind of like that customer I kept showing you. It had all the branches off. That's a star. And so a galaxy is a collection of stars. I swear to you, that's really in a book. And the graph database implementation was that they had a device and multiple devices across different sites that were controlled by an account. And they needed to understand, once you started from an account, how to get to a specific device on a specific site. And so that was traversing through the galaxy by using these black holes, which were just edges. It was a very interesting, there's some physicists obviously on that project, but it was a way to traverse through using strong IDs and knowing where you were going in your path to get the right implementation. And that implementation essentially started from this deeply nested join of, like 20 different inner joins to get the information. And then they extracted it out into the different communities that represented the data, and they gave themselves a path to get through it. And so we were traversing 13 deep, not collecting more data. We were traversing 13 deep and getting it back in about 200 milliseconds. Cool. Mm-hmm.
How can you tell whether it needs to be refactored into a graph database versus just refactored into a regular relational database?
That's a really great question. So the question was, when you have one of these SQL queries with a bunch of deeply nested joins, how can you tell if it needs to be refactored into a graph database versus just a refactoring of the actual tables that are joining? I think that's a great question. And I'm not really going to respond with a black and white answer. Personally, it really just depends on the application. It depends on the size of data. It depends on how much data is coming in and out of this system and how long that query is running right now. Like, is the application having a problem to where if it's taking 30 seconds to get it back out, if that's even the metric, has it gotten to the point where it's a problem? When you're looking at it, was it unintelligently made with tables? I don't know. It's going to require a little bit more, but from my experience, most of those queries are going to be better suited in a graph database, in my experience, but I don't really think it's going to be a hard rule. But it's the first place to start to find something that smells the most like a graph problem. Yeah. Mm-hmm.
Even if you don't really have graph access points as part of your application?
Yeah, I think that's a great question. So the question is that if you're doing mainly graph algorithms, are there places you've seen that storing it in a graph database is just easier because it's the form of the data? I have seen that done for recommendation engines, and that is a huge debate. But recommendation engines, one way to look at it is you obviously have customers and then things you want to recommend to them. If your data is large enough, you would never do that traversal real time. It doesn't scale. You're not going to go person, movies, person, collaborative filtering, yada, yada. It's not going to scale real time. So what we've done, knowing that that is more of a graph analytics problem to do a collaborative filtering estimation, we would store the edges beforehand to say, from this person with this demographic recommend this movie. And so you would go ahead and pre-compute those edges and store them in the database. And I've had some very fun arguments with Matthias as to whether or not we should just put that in a GraphDB or put that in a Cassandra table. So that's an open discussion for happy hour if anyone wants to talk about it. That's an example of where I see pre-computed edges, as well as what we call in the community shortcut edges. If there's a common path you're always traversing, you can leave yourself a shortcut edge. Instead of going 13 deep, you know you're going to go there. You can skip a few hops. I kind of envision all of this work going on with doing paths in a graph database, just like you would do a highway system. If you need a shortcut, just make your road around it. Yep. Well, thank you guys very much for coming. I really appreciate it.